we were talking about LSTM, forget plus input gate. The reason that I mentioned these two gates together is the fact that these two gates create the new cell state. As you can see, the intermediate cell state here. And with the update mechanism of the input gate, the actual new cell state is created as a result of these two gates. So at this point, you know many new things. Well, for example, why the design has sigmoids? Because sigmoid is bounded with 0 and 1. It provides us the fuzzy logic gating capability. And plus we have this 10H and etc. so that we just create the new cell states. And the final state, the output gate. The output gate gets as input not only the input and the previous hidden state, but the constructed new cell state as well. So it uses the new cell, the previous hidden state, and the current input. And how does it use it? Again, with a gating mechanism. So the new cell state creates a new value here, and it's gated with this output gate. So some of it is premed, and you have the new hidden state. So as you can see, the new hidden state is a construction of the current hidden state and the next cell state. I shouldn't have current, the previous hidden state and the next cell state. So this is the working memory. This is the short-term and the working memory. This is what we keep in our mind at that exact moment. This is the long-term information we pass from the previous terms. And the mathematics of it is quite simple. As you can see, input and the previous hidden state concatenated here, fed to this perceptron, this node. So we have some weights with bias. And there is a sigmoid. At this point, we have I tilde, which is here. I tilde is used to fuzzy gate the output here, which is cell state, only cell states vector being applied to the perceptron and an activation function, which is 10H. And you just, again, element-wise multiply it. Some of the elements are gated. I mean, all of the elements are gated. If it is closer to 1, they are let go. If they are closer to 0, they are killed. But if there's some value in between, they are just adjusted, we could say. And you have the new hidden state. Well, when you tell the story this way, it looks, I don't know, so obvious, but nobody did think of it by then. And there's a very funny speech by Schmidhuber. Watch it in 2016 in NIPS, the famous conference. He was the keynote speaker, Jürgen Schmidhuber. And he's a very funny guy. In YouTube, you can find it. If you write NIPS 2016 Schmidhuber RNN speech, you can find it. And in his speech, he talks about LSTM, and he talks about how LSTM is used today, because LSTM is being used everywhere. In Google, when you type something, there is a special LSTM trained for you guys. And he says, he just can't help and say, in 2016, they applied to NIPS with LSTM and they were rejected. Because it's a very new idea. I mean, when you come up with an idea like this, I mean, this is how you can create long-term dependencies in recurrent neural networks. It's quite a bit unbelievable and it's working fantastic. But this is the, I mean, destiny of all good papers. AlexNet was also rejected when they first applied. And AlexNet had some results, even some results. I mean, LSTM did not come up with perfect results. They have practical results, as we know, that, because we know the practical usage of LSTMs today. And at that point, they didn't have it. So one day, if you make a fantastic study, be ready for it to be rejected by us. Anyways, LSTM. So let's make some observations. Just go over some observations we have already made. So during backprobe, for the cell state, there is an open highway. At least there is a possibility of an open highway, because when you're backpropagating, the actuations of the forward pass will also affect the gradients here. It is not an skip connection, entire connection. There are some mathematical operations here. And when you're backpropagating in a computational graph, if there's a mathematical function at some joint, well, it will be affected. The gradient will be affected. However, depending on the values of the gates, there is the possibility of the gradient getting back. Actually, that possibility, that mechanism, helps the LSTM to be trained for longer sequences. So during the backprop, the hidden state is not different than a hidden state of a vanilla RNN. Why? Because the cell state has this gradient, at least the possibility of the gradient. However, look at the hidden state. I mean, it's going to go like this, go like this. It's passing through so many gates, and those gates could be dead. I mean, they're most probably dead because you think of the gradient of sigmoid function and 10H. I mean, it is non-zero for a very limited period. So hidden state is most probably going to die, but it is the short-term memory. Who cares? We have the long-term memory, the cell state, and the gated highway for it to learn long-term dependencies. So as you can see, LSTM is the long, the cell state, the short, hidden state, term memory. That's the idea. Okay, so this is the highway. If you want to resemble it to the ResNet, but it's a gated highway. I would put some traffic lights here. I mean, I shouldn't have said I would because I've prepared the slides. Maybe it was a better idea to put some, because there's gating here. Somebody's gating you, so it's a clever mechanism to let you go, or just because we don't want to always remember what is from the past. When you're doing something, there will be cases that you want to forget something. Can anybody give any example of a sequence where we would want to forget the previous information? Think of a problem definition and think of a sequence. Can you come up with an idea? If you just know it already, you can just say it, don't worry about it. Can somebody give me an example? For example, machine translation, language translation. In most of the cases, you can translate the sentences separately. I mean, there could be dependencies in the sentences. I mean, if it's a very sophisticated text, this could be the case, but let's think about a very simple case. Well, if you're translating sentence, or if you're translating a, I don't know, a conversation, there still could be dependencies, but let's think that the dependencies between the sentences is not to be taken into account. So each sentence is translated separately. So when you have a dot in the sequence, maybe the forget gate forgets everything and starts with a new sentence. Or a better example will be, okay, there could be dependencies within the sentences in a paragraph. However, not everything is to be remembered when you pass to the next sentence. The interdependencies in the sentence itself can be forgotten. So that's what the cell state and the forget gate does. So we need that mechanism. When you're translating a whole paragraph of, I don't know, 100 sentences, you don't have to remember the interdependencies of the first sentence while you're translating the sentence 99. That's what the cell states and the forget gate is for. Okay? I've asked the question, I have answered the question myself. Anyways, I'm the lecturer. Okay, so what about GRU then? We know what LSTM is and we know what it is for. What about GRU then? GRU is like a remastered version, guys. Like, you know, remastered albums. They pretty much sound better, but you don't get the same feeling. It is like that because for most of the problems, LSTM is still being chosen to use, but GRU is more efficient. So this is the architecture. It's a simpler version designed to be more efficient. As you can see, instead of 3 fuzzy gates, sigmoid functions, we have 2. Instead of 2 10H, we have only 1 10H. So it's kind of, I mean, significantly efficient time, like 50% efficient compared to LSTM in computation-wise, because we had 5 gates there, we have 3 gates, etc. And the thing is, we have the reset gate. They call it the reset gate, not to call it forget gate, because that was used, and not to call this input gate, which actually does the update. They call it the update gate. So the reset gate is similar to the forget gate, and the update gate is similar to the input gate. And in the end, we have this 10H to create the output. So there is no output gate. It is embedded within the 2 gates with a 10H function. And actually, the funny thing is, it doesn't have 2 separate hidden and self states. All the short-term plus the long-term information is within a single state. So it is like, I would mathematically imagine, I cannot prove you this to be true, but it is like we have a long vector. Some elements of the vector will correspond to short-term elements. Some elements of the vector will correspond to long-term elements. I mean, this doesn't have to be necessarily true. I mean, maybe a mathematical combination of those is holding that information regarding short-term or long-term memory. I don't know. But you can think of it that way. So the long-term and short-term states are mixed in a GRU. Again, for the sake of efficiency and computational simplicity. So no output gate, GRU only has a single gate. In a way, the self state and the hidden state are one. So let's go over it, just like we went over the LSTM. So this is on the left-hand side, we have the GRU, and on the right-hand side, we have the LSTM. So simple. So reset gate is like the forget gate. It's quite simple, as you can see. I mean, we have the input and the state concatenated, being fed, and you have this. You're multiplying the self state, and you're feeding this, and you're feeding it here as well. As you can see, you can forget the information here. So like this is the combined state vector. The long-term elements are flowing through this part. The short-term elements are flowing through this part you can think of. I'm still speculating, guys. I'm trying to give you an idea of it. I'm imagining that was what these guys did, Cho, the ones who found GRU, thought about when we were handcraftedly designing this architecture. So they created these 2 highways, the open highway and the internal rules for short-term memory and long-term memory, but in the end they combined it for efficiency. Please.
When I hear the term handcrafted, the first thing that comes to my mind is the handcrafted picture.
Yes.
And then how the CNN beat that.
Yes.
Is there a way we can train a machine
yes.
to output such designs which is better than this one?
Yes, your friend is asking from the classroom. Well, when I hear the word handcrafted, I remember CNNs and how CNNs overcome these handcrafted features of pattern recognition. So if CNNs did it to handcrafted features of pattern recognition, wouldn't some idea of machine learning would overcome this GRU and LSTM? Exactly. That's the reason I'm using the word handcrafted here. Because in future, this area is called the neural architecture search. We are going to come to a point where the networks are to be trained as well. That's the next step. And actually, we have so many papers in CVPR, NIPS in 2020 and 21 working on neural architecture search. But it is not easy to find. I mean, never forget that we are neural architectures, which are an output of unique outputs of evolution mechanism, which happened in 4 million years. So it wouldn't be easy for us to find, but exactly that's the next step. So guys, at this point, I strongly recommend any of you who would want to work on neural architecture search in your PhDs, because that's a very hot topic. I don't know if it's going to be the next big thing. That's difficult to say, but yes, if CNNs overcome handcrafted features, someday some neural architecture idea could overcome LSTMs and these handcrafted designs. But this is the best thing we have. And believe me, I did my PhD on that pattern recognition era, and everybody worshipped things like SIFT or Loewe was the great guy. He was a great guy who designed the best feature. Nobody's talking about it today. So exactly. Someday like 5 years from now, I'm going to be lecturing something and I will be just smashing LSTM and talking about how a bad design it is, because that's the evolution of it, exactly. So any questions from the Zoom audience? Okay, good. So that's quite a comparison. So what about the output gate? So the output gate is actually embedded within. It's a creation of the two gates. Okay, you may have already realized that there is no hidden state. And remember that LSTM output gate's purpose was to calculate the hidden state. So no separate state, no separate output gate. Let's use the 10H to create the new state and gate it if we need it. Okay? So the idea is simply the long-term dependencies will flow from here. The short-term dependencies will flow, the working memory will flow through this roads, to these two roads. It's quite similar to LSTM, an efficient version. Still a very good idea, guys, because it is experimental results show that in many problems, GRU is working very similar to LSTM. Actually, next week, I'm going to be doing a live code in Show and Tell. And in that, the original paper is LSTM, but these guys who prepared the GitHub codes created a code where you can try LSTM and GRU and etc. In their results, GRU is working better. So working better, slightly better, but with less computation, which is something very important. I mean, we're going to be putting these things on edge devices like GAVs, and less computation is something very valuable to us. So GRU is also a very important paper, guys. Also, although it's a, it's a limited contribution over LSTM, still very important. So why no hidden state? Then GRU's single self-hidden state is vectoral. Some elements of the single vector include both the long and short-term components of the sequence. So how does this compare to LSTM in practice? For that matter, LSTM becomes more transparent. So we know LSTM, what part of the network, what part of the states is long-term, one part of the states short-term, but still we don't know what that long-term means. So states being transparent doesn't necessarily mean what those states are being used for. Still not transparent that much for that matter, but still in GRU, it is combined. But GRU is more efficient. 3 activation functions compared to 5 activation functions of LSTM. Okay, in practice, they perform similar, although LSTM is believed to perform slightly better in many problems, but there are problems where GRU works better as well. Their comparison is a detailed subject, which we are going to be dealing into a bit. I mean, not dealing into, we are going to go over some papers. We are going to say, it's happened here, this happened there, kind of. Okay, there's a nice paper discussing these guys, and these are the gods of deep learning. So Yoshia Bengio. The first thing they asked was LSTM or GRU. And here is the link, and there's a blog discussing the discussion. I mean, you see nowadays people in AI publish papers, and when they publish papers, the bloggers, AI bloggers, race themselves to write the best blog to discuss that discussion so that it is easier to understand. So it is like a translation from paper to everyday life. And there's a blog for it. The empirical results do not seem to be enough to declare a winner still today between LSTMs and GRUs. And this suggests that either one or other might be suited for a given task. So what I do is, if I'm going to use LSTM or GRU, I definitely try both of them. Definitely try both of them. Actually, we've done work on dynamical systems. We tried them both, and they were practically the same. They had some little differences. LSTM was better, but practically the same. Okay, LSTM GRU. So, okay, so LSTM was an handcrafted design. Like 20 years later, people come up with an idea which was more efficient. So maybe there could be other ideas. So if LSTM is an improved handcrafted design for NNs, and if GRU is an improved version of it, there could be other ideas, right? We could change different things. What we could make it more accurate, efficient, or maybe make it more complex for some purpose, I don't know. What to change then? the architecture, just like the GR you guys did, activation functions, input-output flow. I mean, because when I look at this design, those are the things that I can think of changing, right? There are LSTM variants, guys. There are a lot of LSTM variants. I'm going to go over them today in this lecture. Before that, one final slide. You see, in one of the revolutions of LXNet was using the ReLU, because ReLU is an activation function which is very easily differentiable. The derivative of ReLU is 1 if the activation is positive, 0 if the activation is negative. Quite stupid. And if you're doing backpropagation in large batches of data, for example, in a GPU, this is something you don't have to code. It's an if-else function. In microprocessor terms, it is like a jump instruction. So that fast. A jump instruction would mean microseconds, nanoseconds. So that's why we are using ReLU. That's why we are using GPUs to train CNNs. It is. But if you check 10H and sigmoids, and they're slow, and if you remember the history of CNNs, well, we never use sigmoid or 10H in CNNs. So they're in the rubbish bin for CNNs. So why not? Well, that's a discussion as well. There are papers for it. We are going to talk about them. However, do not forget that these guys having sigmoid and 10H has a purpose. This is a handcrafted design. This has a purpose. This is a sigmoid because this is a fuzzy logic gate. It needs to have a value between 0 and 1. And ReLU does have values between 0 and plus infinity. And 10H, again, a bounded function between -1 and +1, a symmetrical function which is symmetric at the origin. This is also important. ReLU is still not a symmetric function. So if you use something like ReLU, all your activations will be positive. That's not something you would want to have if you're trying to build up a handcrafted design like this, a balanced design like this. So people ask the same questions for CNNs and multi-layer perceptrons, or also called fully connected layers, dense layers, whatever. ReLU work perfect. What about RNNs? I mean, can it work? Just like I said, the usage of sigmoid and 10H is a handcrafted design. And the fact that they are abandoned in CNNs is about 10H and sigmoid creating the vanishing gradient problem, right? However, in LSTMs, that problem is solved with a different solution, with the gated highway. So if the gated highway solved the vanishing gradient problem, so there's no harm in maybe using sigmoid and 10H. That's why still today, we don't have a ReLU version of LSTM, because the bad side of this activation functions were they had 0 derivatives around here and here as well. So this is derivative functions. So they are non-zero for a very limited period, which is the manifestation of the, this is the cause of the vanishing gradient problem. So why not use them for LSTMs? Because LSTMs solve that problem with an architectural solution. That's why today we have people have tried ReLU LSTM, but the original LSTM design is still more powerful because we have fixed the problem of vanishing gradients with an architectural solution. Okay, good. The fundamental problem with RNNs and ReLU's partnership is not related to gradients but values. It's a handcrafted design, and the things that I've been talking about in previous slides. Just like I said, it needs regulated values, and the vanishing gradient problem was solved in an architectural manner. However, of course, Geoffrey Hinton thought about it before all of us could think about it, and they published a paper. So they come up with this idea. They used ReLU in RNNs and how to just initialize them and use it. So they propose a relatively simple solution that use RNNs composed of ReLUs, not LSTM RNNs. They aimed at exploring whether ReLUs can be made to work well with RNNs Their solution was the initialization trick. They said that, again, remember the identity RNN. It is similar to that. If you make the initialization correctly, it can work, they said. So we come up to this point. In RNNs, the activations or the activation functions, whether ReLU or 10H, if you want to make them work, you should be able to train them. And to be able to train them properly, the capacity is to have those networks have a proper gradient flow during backpropagation. And since recurrent neural networks, all deep neural networks are actually dynamical systems, you can think of a recurrent neural network like an ordinary differential equation. Actually, we are going to make that similarity, work on that similarity in this course in the following weeks in neural differential solvers. So recurrent neural networks are like ordinary differential equations. You have an initial state, you're evolving that initial state on a function. So what is the trick of converging, you might ask, because those problems are similar, ordinary differential equations. The trick is to find a good initialization, they said. But this is a mathematical analysis, guys. This is not like a practical engineering solution. This won't help you with the real world machine learning problems. And you have got data. How am I going to find a good solution on it? Let's make a good initialization. That's not the way to do it. You need the right architecture to do it. What I will say is finding a good deep learning solution model is an architecture problem first. Then it's an optimization problem and analysis problem. You need the correct architecture first. Okay. And what also they say is they also claim that their solution was comparable to the implementation of LSTM. So sometimes it's not. This I don't believe that is entirely true. Is it true? Most probably yes, for a limited problem set. What about general problems? Well, that's the beauty of LSTM and GRU. They kind of work on everything. And we're going to see that. I mean, until transformers in this course, we're going to be working on LSTMs. And for the problems that transformers cannot solve, like, I don't know, dynamical system modeling, etc., LSTMs still rule. So they're very powerful. And this paper is from 2015. People still use LSTMs without ReLU. I think it proves the point. And most probably the idea was good, but not strong enough. It was a nice analysis. In today's AI literature, LSTMs are a de facto standard. I mean, I put a question mark here because we are going to be seeing transformers, and we are nowadays going through a very, we are going through a change. People are working on transformers. Transformers are very hard to train. They need a lot of computational power. That's why only some groups can work on it, and we are getting some results. We're going to see about it in the following year. So these slides and the discussions we do this year might change when I'm doing discussions next year when I'm lecturing this course, when it comes to transformers. However, the fact that LSTMs rule is still correct today. Okay, so talking about ReLU, let's talk about other activation function. There are zillions of activation functions, because anything could be an activation. If it's nonlinear, it could be an activation function. And actually, in the history of neural networks, people have worked on different activation functions. Okay, we could try a different function. I mean, maybe we could try a different function and test if LSTM works better. Well, people have already done it. And again, before we could ever thought about it in our brains, Jeffrey Hinton and their group thought about it, and they did it. They published a paper. There's a practical paper by Farzad et al. In 2019. They try all of them, almost all of them, 23 different kind of activation functions. I mean, anything could be an activation function, but when it comes to activation functions, there are certain needs, like they are being bounded, because when they are not bounded, things can explode, and etc. Their results exposed some less recognized activations, such as the Elliott function, etc. They could yield to some, degraded errors for some certain problems. These are nice analysis, but in general, the winner was LSTM, the classical LSTM. So it's kind of, classical LSTM still holds the title, guys. The actual rival to LSTM could be thought of a GRU, is more like a partner to it, but maybe a transformer. Transformer you don't know now, we're going to talk about later in this course. So it's not the activation functions then. Let's continue brainstorming on it. What kind of modifications to the original LSTM architecture have been suggested, can be suggested? I mean, if it's not the activation function, next thing that comes to my mind is the architecture. Maybe we could make some other connections, and because the handcrafted design was mostly the architecture in the LSTM. Of course, there's the gating structure and using sigmoid and etc. But what kind of architectures we have? Well, it comes to me as a surprise that LSTM, the classical variant, continues to achieve the state-of-the-art performance after 20 years. It's still holding the title. So that being said, let's go over the variants and let's go over what people have worked on, because that's how we do science, guys. That's how you go over the literature, try to understand what people did and what contribution that experiments provided us or not provided us, so that we could come up with our idea, which may be the next big thing. LSTM variants. Again, the guy who has found the LSTM, Jürgen Schmidhuber, thought about it before we thought about it in our dreams. Thinking about better variant for an LSTM. And they published a paper. This one, I strongly recommend it. Find it in the additional reading, I put them. They've changed things, they've compared different variants. There are a lot of variants of LSTMs. And actually, I can safely say that the classical variant still holds the title after reading these papers, guys. In the end, LSTM classical variant is good. But what people thought of and what were the ideas? Let's go over them. So the classical LSTM, the one. The GRU, the efficient partner, the Chinese one. Saying the Chinese one was something like a bad adjective, like maybe 20 years ago. Today, it's something good. When I say the Chinese version, I mean it's the better one. Well, the next thing is the people LSTM. As far as I remember, it is from the original group. So maybe we continue with this one. The people LSTM is a simple architectural variant of the classical LSTM. The classical LSTM overcomes the problem of gradients vanishing in a recurrent in an RNN architecture by connecting some points via persistent cell state, where the cell state can flow back uninterrupted by anything, if that's what the gates decide. However, the gating layers that determine what to forget or what to add, the gating, fuzzy gates, don't take into account the contents of the cell itself. If the cell is evolving, right? What about what happens if we add connections that allow the gates to not only depend on the previous hidden state, but also on the previous cell state? As you can see, this cell state is constructed by these gates. These gates are only constructed by these inputs, not the cell inputs. What about we feed the intermediate cell states to these inputs as well, or the previous cell state? What happens? Will it help? Because in the end, it's an additional architectural connection. And when it comes to training, what will happen is the backward gradients will be routed in some new directions, because there will be connections, right? That was the idea. So this is the people LSTM against Schmidhuber, the original guy. And that was something they've tested. And what they did was they created this so-called people connection. The people is that hole you have in your front door in your houses. So that you could look at it. So you could look at the cell state and get some information if you can. They created these people connections. So the previous cell state being concatenated for this state, okay? Or for this state, or for this state. As you can see, this time we are feeding the intermediate cell state, guys. Okay. Sorry. So let's see what happens mathematically, because it's something simple. Previously, we didn't have this, right? It was the previous cell state. What I'm doing is, I'm not doing it, this Schmidt-Huber and these guys are doing it. They're concatenating the cell state as well, feeding it to this network. So the capacity, this network would grow because you would need more weights for it. And the forget operation is decided with this operation. So the forget gate is modified this way. Or you're feeding this state, sorry, to here as well. So again, for this gate, the concatenated vector does not only include the input and the previous hidden state, but the previous cell state as well. So again, the cell state will be affected, right? And again, for this gate, the people connections are to the gates, to the fuzzy gates, the sigmoid gates only. Be careful, not to the 10H gates, the sigmoid gates. So it is trying to construct, they are trying to construct a mechanism where the previous or the intermediate cell state will affect the gating mechanism only. That was their idea. And they discussed this in their paper. I strongly recommend if you're interested to read it. Again, you have this. Why? Why would you do this? The original paper is called Learning Precise, you can achieve a precise timing with LSTM recurrent networks. As the name implies, the idea was to create a precise timing. If the input-output sequences that you are trying to create, I mean, I don't know what you are trying to, what you will be doing in your projects with the people LSTM, but it will be a sequence problem, right? Something is flowing in and something is getting out. It could be a sequence or some classification value, whatever. For sequence-to-sequence problems, if the timing is important, if you want to see an effect of the input sequence faster and exactly maybe at the same instant at the output, they've come up with this results, come up with a group of results that if you use people connections, you would have better and precise timing in these sort of problems. So it is like a finer distinction of changes in the input and hence the states. But that makes sense because if you feed the internal states and the previous cell state, more information will have a more sophisticated representation at the output. And I mean, it makes sense after they published the paper, of course. If it makes sense for you, publish it yourself, you could have said, yes, you're right. But I'm trying to make a sense out of it. That's why I'm saying that. So that was the people LSTM idea. Any questions about the people LSTM? It's the first architectural variant we've seen.